First of all, I'd like to thank you, Laura, for coming. I will talk about my courses, and these courses will be on devices physics of electronic and optoelectronic materials. If I point here, just you can see, the people online can't. But if there is some issue online, please, who is seeing now, report to me if there is no option to see something that I'm talking about. The courses will be devices physics of electronic and optoelectronic materials. We start from crystals and go to amorphous and functional devices. I'm Professor Louana Wouk from Brazil, Institute of Physics of University of Brasilia, and now I'm here in France as visiting professor junior because I'm less than 10 years of PhD, and I'm working in Sargi Université at LPPI laboratory. So in Brazil, I'm coordinator of laboratory of optimization of technology for sustainable use, Lotus. It's some short name of work it. And here are my group here. Maybe someone is missing, but some of them are in undergraduate program or masters or PhD or postdoc. So here we were organizing an event, local event. So this is why we were dressing this H2 tech. That means technology for hydrogen generation, storage, or sensing. And just to give an overview of my background, I finished my PhD on Sweden and UFPR in Brazil in 2018. And then I started a position on ONIM, that calls Center of Innovation in Brazil. This Center of Innovation is like some non-profit employments with working on research basis and applied for devices. Then in 2022, I started my position as associate professor at UNB and the coordinator of the laboratory. And since last year, I'm here as visiting professor. And my main projects are the Midwest development, that this is the reason I'm here, because of this funding. Is the funding for improvement of Brazil Midwest region. And then I have also funding for my laboratory called INCT NanoLife and the project Human in Nanoscience. Here are my contact if need anything and discuss anything regarding the presentation or the research. And our laboratory Instagram, where we share some news over there. Just to give an overview on why we are studying these materials for devices. Here are one of example of devices that's called photovoltaics, where we convert light into electrical bias. Here we can see during the years since the discovery of electrovoltaic could be storage in electrical bias around the 70s. We had a huge increase in efficiency. We can see that this is the NRL chart, where we can see all the efficiency of devices and the relationship between the structure of devices, the material that are using, and also some new technologies that are emerging. So here we can see that it started with these green dots, and when we see the green are thin films technology. That means the photovoltaics are SIGs concentrator or just SIGs without concentrator, or cadmium tellurium, or amorphous silicon that is stabilized. The another kind of structure of photovoltaics are crystalline silicon cells that has higher efficiency from the starting and goes increasing over the years. And this crystalline differs from those crystalline that are in purple. Just the structure, these are single crystal, these are multi-junction or more than one semiconductor on the same devices. So if we see over the years, we started the silicon and another inorganic materials, and everything was going well. So since then, we could apply it commercially. So we can see over the houses, the buildings that has photovoltaic technology everywhere. So the reasons behind of those devices improvements were the understanding behind the materials properties and the relationship with the photovoltaics. Among the years, we could see that around the 90s, we have emerging PV. So these emerging PV are some new technology that we call fourth generation technology of photovoltaics. In these materials increased rapidly because of the acknowledgement that were previously understood on inorganic, for example, materials. So the efficiency goes high in shorter time, but this improvement in efficiency goes directly related to the acknowledgement behind the device's physics of high inorganic materials. So this is the reason that our courses will start from inorganic materials, inorganic devices, and then we go to organic emerging PV technologies, and not only PV, but also LED or sensors and transistors devices. So the course description will be holding 26 hours. It means 13 Tuesdays at same room and the same hour. The focus on the course will be on fundamental physics that governs behavior of materials used in modern electronic and optoelectronic devices. So I gave an example on photovoltaics, but also on LED, transistors, sensors, and other kind of devices. And we start from crystal bond that I briefly discussed it today, and goes to charge transport, structure, bond structure engineering that rule the device operation, and the relationship with the materials, for example, magnetic, diamagnetic, dielectric, metals, materials applied in those devices. So here are the topics of the 13 days that we are discussing. So today will be an introduction of materials that we will see around the days, the course. And I will start with a brief of crystalline structure and the reasons behind the atomic behavior of the materials would affect on properties that we must choose for those devices. An overview on quantum mechanics to start electronic properties of materials. How we can build the electronic band structure. So the 30-day will be focused on this, studying covalent, everything on the inorganic materials, covalence band, and further. Charge transport and semiconductor and metals, which means that junctions, how it worked in junctions, how it worked when we mix some semiconductor and with metal, because this will rule the devices that are made by diodes. The fifth day will be on transistors, how to operate one transistor, what is kind of the transistor historically, and nowadays what are the new transistors based on inorganic materials. And another optoelectronic devices, that means photovoltaics, OLED, LED, and photodiodes. And the second part of the course will be on disordering, which are the most popular material of the students, using polymers and organic molecules. So here I will discuss the electronic properties of organic molecules, how are the charge transport in organic materials, how the interface in charge injection in organic. When it goes to organic devices, we must discuss regarding the flexibility and how it could affect the organic devices. And we finish with stability and degradation tests, together with some characterization techniques in organic films. So just to give an overview on what we are doing. Before I start to talk about it, I would like to ask, are you what level of PhD student from which supervisor?
Sophie.
Sophie? Okay. So are you working with polymers and ionic polymers? And online, I don't know who is just if you guys can tell us who is online and what are you working with, and what kind of material. Your search, your focus is on developing new actuators?
I focus on polymer solution for longer film, like PhD.
Also, it is more on synthesis?
No, only the structure and the chemical labs.
Okay. And applied for some specific.
It's very theoretical.
Theoretical. Okay. So more on modeling than on modeling of the charge transport. Okay. And João, I know that João is online. Can you hear? I don't know, Luis.
Yes, I'm here.
Okay, so Luis, introduce yourself, please.
Hello, everybody. My name is Luis. I'm studying, undergraduate studied, and I work with perovskite solar cells, basic crystalline structure.
Okay,
From
thank you.
Brasilia, too.
I have some students that are online. Davi, Davi? I will just see if it's some. Uh, they said that the interconnection is not working very well. Matthew Harris. I don't know if I pronounce it properly. Matthew? Do you know Matthew? Hi, Matthew. No. Amer? Hi, Amer.
Hi, my name is Ahmed.
Okay. Can you introduce yourself, please?
I'm studying in UNB e acho que é isso.
Amer is working with organic solar cells. He has a background on transistors, right?
Yeah. Tem.
And now he's doing PhD with organic solar cell devices. Davi, the last that I can see there. Sorry, guys, that I caused you some trouble, but it's not a problem for communication. I would really appreciate if we could share, but if it is not comfort, I think you cannot talk, no problem.
Hello, Rini.
Hello? Who is calling?
John.
João?
Oi. Hello, everyone.
Hello.
My name is John. I am postdoctoral student. My focus in simulation organic materials, applied of organic solar cell, hydrogen evolution, and synthesis of materials.
Okay, João. Thank you. João also works with modeling and also working with experimental materials in the devices construction. So just to give an overview, so we are in Paris, around Paris, and I'm from Brasilia, that in the Midwest of Brazil, so more like this side of Brazil than here. Brasilia is the capital of the Brazil. Even though Rio de Janeiro is the most popular city, Brasilia is the capital. And this is an overview of the city, that here are the Planalto Central, that means all the governmental politicians are working, or we hope that they are working there. And then the university is near this side, and we have this huge like summer weather every day of the year. So even the winter is not so cold as here, but and here are some images of the city and the pilot plan that were the basic foundation of Brasilia. It means that our cities look like a airplane. So we are in North Wing here, this is the university, and here are the Monumental with politicians, and here are the people that live nearby the Eixo Monumental. And some beauties of our city in Brazil. And here are our university, UNB, where you can see that a lot of green plants. And the people here, our institute are in the ECC, that means Instituto for Science and exact science. And here are the people with a lot of background, not just in physics. And yeah, in UNB, we are focused on studying organic materials, which is the reasons of our discussing on the course. But why we started to work with it? Organic materials can be applied, as I told, in photovoltaics, and also working on several kinds of devices. And the devices can be developed to harness and renewable energy sources, which means that we can convert light from the sun or the internal light into electrical bias. And also we can provide some sustainable alternative to traditional fossil fuels. But organic materials are not just focused on these new systems, because we can see that there is not just organic materials that could be applied on it, but also inorganic and other system. But they have some peculiar that can be operating on lower energy consumption. So we can construct sensors and OLED with low energy consumption. And also during the fabrication of the materials, we can use some manufacturing that could be done on large area that we called, which are the slot die devices here for one example. And we can print all over in large area these devices using those organic materials, due to lightweight, flexibility, and they also can be applied in diverse surfaces. For example, here we just grab some, this is photovoltaic, but we can cover some surface with it without any problem because of the flexibility. To construct those devices, the materials must be soluble, and we must do it through techniques that call solution processed films. These techniques are not the only one that could be done, but this could be one of the most cheap techniques to produce semiconductor in large area. So here one example are spin coating, where we can spread one solution over a substrate. Those substrates can be turned and spinned, and this depending of the relationship between the surface energy, the film, the solution concentration, the dynamic of solvent evaporation, we can spread those materials over the all substrate. These are one of the most popular solution processing film for organics, but in large area we must change it to meniscal guide coating, which means that we must cover a surface using a knife where it can spread the solution over all substrate, and we have different dynamic evaporation than spin coating, but also can be related microscopically related to energy of substrate, to interaction of solvent for evaporation, and the properties of the material that are dispersed in the solution itself. This menisco-guided deposition that we are focusing on our laboratory can be, for example, used in one printer, and we can print the technology just in our printer, common printer or inkjet printer. And also we can apply the over roll-to-roll process where we can deposit materials over several steps. So the devices that we are focused, sometimes we not just use one material itself. We must use different materials to improve the efficiency, to charge collection, to charge transport, and they also improve the stability. So each step of the device, which means not just the position, but deposition could be more than one step. Patterning, that would be the design of the electrodes, and also packing, which means that we must increase the stability with packing of those devices. Here one example of the already commercial OPV applied in several kind of the surfaces. Here the OPV, for example, are lightweight, flexible, which we can see further that with silicon-based materials we cannot have this kind of devices. So the strategy to include organic over the silicon is not to replace the silicon, but to use with new design and new devices with different architecture, which could not affect the building and not affect the, for example, the surface that I will cover. If I use, for example, solid PV, I will just lose the beauty of the tree that could be done with the organic devices. Organic and general PV devices are made layer by layer, which means that we must use different materials with different properties, and these different properties would generate the charge and transport the charge and collect the charge, each one in their specific electrode. So here are one example of the materials that we work, organic materials. For example, we will use some polymer mixed with acceptor materials. In this mixing, we have some active layer that we call, which are photosensible, It means that when we absorb light, it creates extons and will be dissociate on the interface. The interface of dissociation and transport must be reduced, the resistivity, so we will include the electron transport layer and hole transport layer. So we reduce the charge transport resistance to collect the hole, for example, in the metal and the electron in the substrate electrodes, transparent electrodes. So here are the overview on our focus on our group. But to understand the reasons behind why we must construct sandwich layer, why we should use this material, those materials, or the new perovskite material that has near close relationship between the organic performance. Everything that were designed was previously designed by the inorganic materials that I said earlier, and everything that we are focused, we must look into material engineering. That means if I change something in the molecular position, I can increase the efficiency, or can I increase the stability? The interface engineering, which means if I have charge transport and charge trapping here, it will increase or decrease the stability. Everything focus on enhancing the energy conversion efficiency, that is the most seeking for the materials properties, but also the improved stability and durability, because nowadays the highest efficiency for photovoltaic, for example, is beyond 20%. So 20% is really nice, the conversion of the light into electrical bias. So we must focus on how we improve the stability of these devices, and also how we could decrease the cost, because sometimes in academy we don't think on cost, and this is one of the most important things nowadays, because if, for example, seek for new atom or new molecule that are hard to find or to the synthesis will be too cost, is not suitable for large area manufacturing in low cost devices. And the overview on flexible devices that we can apply in some infrastructure that already exists. We don't need to change, for example, the background of infrastructure to increase the stability of the photovoltaic modules over the ceiling, for example. So here the operation overview. Why I'm talking about it, I would not talk about our inorganic materials. I just give you an overview. This is what we know now, and how we could, how we construct this overview. It will be answered during the whole course. So this is what we know now, and why we know now, why know this will be shown in the whole course step by step. So the photovoltaic devices operation using organic materials, it work with the semiconductor that I said earlier. It creates an exton, that means is electron hole pair that are Coulombic attracted, and this binding energy must be broke in order to have electrical bias, which means one electron to one electrode, and the hole, that is the absence of the electron, goes to another electrode. So here the electron being the energy, we can split this exton, giving another new material that we call acceptor. And this acceptor material must have a donor acceptor electrical dipole, intern dipole, where we can broke this energy to electron going to acceptor and hole staying on donor material. So here, after we broke this electron and hole pair, we must conduct the hole to the interface where it has the cathode, and the electron goes to anode. So each step, if I improve the absorption, if I improve the charge separation, the exon separation, the charge transport, or the charge collection, each step will directly affect on device's performance. And also, if I reduce the resistance between one of material that I used, will also improve the efficiency and stability. Nowadays, the most popular organic material are fullerene materials, but they were replaced by some called non-fullerene based photovoltaics because of this reducement in energy needed to spread to break the exon. I said several words that I didn't introduce earlier. So during the course, I will explain what are extons, how are they binding, how is the energy between them, and how they are migrate and charge transport between organic materials and inorganic also. So this is just an overview of nowadays understanding of organic. So as I told you, inorganic materials were the basis concept for developing the devices on organic materials. So to understand the first principles of the materials, we must look into atomic energy and the atomic binding between the atoms itself. So for example, the chloride sodium. When we have one atom, it is just an overview on the chemistry, basic chemistry that we can see on the, I think, background in some physics and chemistry backgrounds courses, but all atoms must seek their lower energy, and to seek their lower energy, the sodium, for example, tends to lose one electron of valence, and it becomes sodium positive because the charge will be positive charge balance between the atom. And the chloride, the chlorine tends to gain the electron and becomes the ion chloride minus, which balance negatively. So when they have this difference on the polarization, they will attract each other and form ion attractive due to oppositely charged. So the most stable will be attracting the electron of sodium, and the chlorine will be filled with this electron, and the sodium will be filled the last valence, the valence band, because the sodium donates the electron to chloride. So the stable form would be ionic lattice, where we can see atomically. I will just give everything here because in terms of energy, the energy are lower when ions are close together instead of the charges, the atoms separately physically. So to see it, I just introduce here one graphic. So here we have the potential energy and the distance, internuclear distance, which means the distance between the center of sodium and chlorine. And when we increase the distance, that we broke the binding energy of these atoms. They are free, but the energy of the itself, they themselves alone are higher than when they are together, because of the attractive potential between them due to different polarization of charge between chlorine and sodium. So the minimal potential means that the more stable energy for those structure. So if we decrease even more the distance between them, we could somehow mix those atoms. So the energy curve will increase significantly. So this means that has repulsive interaction. If we could mix them, we do have a fusion, and nuclear fusion, but we can't because of the energy of mixture. Those two atoms will be extremely high. So in terms of nuclear distance, there is some minimum distance where these distance are the medium between the close and the separately, but they not be broken those binding energy. I don't know. Sometimes okay. I think it is because of my slide transaction. So in terms of distance, how the atoms can be arranged in order to have minimal distance and lower energy. So this goes to crystalline structure, where we can correlate the atomic bonding and the atomic I just spread everything. Through crystalline structures, so where we can have an energy, or a minimal energy that is the distance between those, for example, chloride, sodium, that are they together. And this distance, we can calculate it using some quantum mechanics theory, but just to give overview on crystalline properties and the correlationship between the materials that we investigated with the ordering that we have. So when they have ionic solids, which means that the ligand, the binding between those two atoms are ionic. So they have too strong interaction between two atoms. Is quite hard, is not, but it's quite hard to break those distance because of electronic interaction. So they usually have a high melting point, and also the electrons are strongly bonded to ions, and this could have low electroconductivity and low thermal conductivity. So the materials that has ionic solids, they are very good isolators. So we can apply it in different step of device construction because of those isolate properties, and also low thermal conductivity. It means that they have some, they can block the thermal conductivity between the molecules. And as they have absence of free electrons, that means that they have good optical transparency, which means that the band gap between the bonding of the atoms is there is higher energy than visible light. So one example of these solids are chloride, sodium chloride, potassium chloride, sodium bromide, and in oxides, zinc oxide, titanium oxide, and some sulfates in selenites. Materials also behave like this binding energy between those atoms. Another kind of bonding are the covalent bond, which the materials can share the electron between different atoms. So the electrons are shared between atoms that are near each other. The sharing of electron goes through attraction from the presence of electron between the atoms. And this would also happen in the case of spin antiparallel. I will not start with these terms yet, but those antiparallel systems of electron must be ruled to have a covalent bond between those different atoms. And the physical properties of materials that has this kind of bonding has lower melting point than ionic, because it's easier to break instead of ionic compounds when comparing them. But they are they are together with the ionic bonding and materials that have an ionic bond, they have a very stable structure. And for example, here, who has covalent bonding are silicon, germanium, cadmium, calcium, and gallium arsenide. So how they share the electron? So in this case, we have, for example, here, a cloud, electron cloud over the one atom, hydrogen atom, and a fluorine atom. And these cloud are the valence cloud of them, and they are binding due to electron sharing between hydrogen and fluor, and the overlap between the cloud, electronic cloud over the materials. We have this overlap between valence orbitals, and depending of the properties of atoms, we have different overlapping of these orbitals, which means that depending of atom, we have more electrostatic electroaffinity, or and we can easily break or not easily break those ligands between different atoms. So in terms of energy, as the same as ionic, where in here we have this hydrogen molecule, is more stable when we share the one electron each other. So the distance in hydrogen, the minimum distance in hydrogen is the radio of 7.4, and the lowest energy of these molecules in the hydrogen, they can be used for to ligand, to bind with another atom as fluor, as iodine, as carbon, and further. Okay. So still talking about covalent bonding, we have some regarding when we talk about carbon, basically, we have some theory behind that we will discuss it more in the second half of the course, but I will just give an introduction here. Are the sigma and pi bonds formation, single, double, triple energy depend of the hybridization of orbitals, and this hybridization and geometry of orbitals impact the stability and the energy of those carbons ligands binding, and the electron density distribution of different hybridizations also impact the conductivity, polarizability of the atom, and this energy between ligand states and anti-ligand states, we have some band gap, which we can construct the base of semiconductors materials together with the silicon and germanium atoms also. Despite covalent and ionic bonding, we also have molecular bond between atoms. Molecular bonds are very weak interaction between molecules. They usually happen between two different interactions. For example, here, we have covalent forces that are intermolecular forces of two atoms. And when we have parallel or different symmetry of them, we have interaction between the neighborhoods, but they cannot bind with another atom because they are really in the lowest energy. So we have intermolecular forces that are interaction between, for example, this atom here with this, that are the polarizability affinity are welcome to the atom, and these binding here are usually van der Waals bonding or another kind of bonding, which can easily break with minimal forces between the intramolecular forces. So it starts from dielectric dipoles formed by those different dielectric properties. And we can see it on hydrogen, on the carbon dioxide, oxygen, on the 2D materials also. And for example, here, I just got some figure in the internet that I like it to show. And here we have some stable structure, for example, chlorine and sodium chlorine, but they attract each other because of the van der Waals forces, and the distance affect the strength. So if they are close, they are stronger than in the distance are related for one inverse of 6 potential of the distance. And there is not just van der Waals type of forces, but also dipole-dipole interaction, London dispersion forces, and hydrogen bonding. So these are the forces that are weak, but we can see a lot of materials, and these materials are nowadays gain increasingly focus on their application. And here I show one application of van der Waals interaction when we use the atomic force microscope, for example. Here we have a tip where it can be vibrated. This tip can have some fundamental frequency, and depending of the surface and the energy of the surface of the atom that are in the surface, the tip will be attracted and will be dephased on the frequency, the natural frequency of this tip. So we used this van der Waals interaction between atomic force microscopy to analyze the surface, not just to design the devices, but also to investigate microscopically how the materials are organized. And the last bonding are metallic bonding, which are the materials, the bonding that could be found in materials for the optoelectronic devices and electronic devices. So in metallic bonding, we have a sea of electrons. This draw here is just overall, but there is a lot of electrons free here. But what we can see that easily can be conductive through electrobias or through difference in thermal gradient on these structures. So the electrons are free to get locomotion over the several atoms and form a partially filled electronic structure. So it's called Fermi C. And this usually happens when we have a crystalline lattice that we will talk more about it. But the energy of ionic and covalent solids are lower than ionic and covalent solids because of the easily to break these this free electron. Although they have a really high conductivity, a really thermal conductivity, because of the electrons can be also carry significant kinetic energy. So depending of the bonding, the atomic bonding, molecular bond of materials, we can use the material with some different aspect, with a higher electroconductivity, with lower electron conductivity, with higher transparency, with lower transparency, or with higher mechanical resistance or lower mechanical resistance, depending of the properties of the device that we are seeking. So to understand how the bonding are done, we must go deeper into crystalline structure. So the materials are organized in three kinds, basically, of structure: crystalline, amorphous, or polycrystalline. The crystalline solids, they are arranged in atoms in a periodic and repeat lattice. So the crystalline ideal crystal means that we have the same structure without any break. So the repetition will be infinite of same unit cell, and this defines crystal symmetry properties. And the amorphous means that we don't have any kind of periodicity. So it can be just a random and chaotic arrangement. For example, here we can, in crystalline solids, are the sodium chloride, and the amorphous solids are the polymers, glass, and amorphous silicon. Amorphous silicon actually are between the amorphous and crystalline, are more polycrystalline than just totally amorphous. But polycrystalline solids are basically with small crystalline regions that can be organized differently depending of the crystal growth or the crystal stress that it happened during the film deposition or crystal growth. Here, for example, we have the crystalline structure where we can see that are ordered. So we have some pattern between the atoms position. These positions are ruled because of the minimal potential energy between them. The amorphous are randomly organized, and the polycrystalline are different grounds here, grains, where they have specific properties that could be some specific electrical property or some magnetic property with different atoms or some different defects. And to understand how these crystalline are organized, because amorphous are ruled by other kind of theory, and polycrystalline are in between the crystalline analysis, but we must understand what is lattice and what is unit cell, which lattice is a regular periodic array of points in space where represents the atomic position, and unit cells the smallest repeating structure that defines the crystal geometry. So in this case, here I just translated because it was in Portuguese, but the crystalline periodic and the amorphous random and the many small crystals that are part of crystalline. So the unit cell, for example, we can compare, if I can. Okay. For example, if I have some lattice here with points that organize my system, and I know that each point has some basic ions or two atoms, we can organize these atoms periodically over this primary cell that are the basic of the organization of solid states. And these atoms, they can be, for example, diatomic, but also can be more atoms than just two. To seek some figure that could represent or crystalline structure with different kind of unit cells and bond and atomic bondings. I saw this in internet and I was really I thought that it was nice because we can represent this atomic ligand, for example, with this draw, and the unit cells are this geometry where we can put in one side of the unit cells, and if we repeat it constantly, we can have this kind of image. And if we have different geometry of atoms, for example, this draw here, and we have a different organization of primary cells, we can spread over the position of the atom here, the primary cells, and have this draw. So sometimes it's not so easy to find the unit cell of material. It's quite hard, actually. We have some in study solids, some applications where we can draw the distance between the fundamentals of the atomic. But sometimes, depending of the interaction of the atoms that we are seeing, is more comfortable for using some molecular modeling to seek the unit cells of the new material, for example. But just to give an overview on how it works on crystal lattice, unit cell and primitive cell, atoms can be arranged in space in different ways, as I told earlier. And the distance between the atoms and the origin, we can coordinate it with some coordination using three vectors that are A1, A2, A3. And these vectors can be described using periodical crystal described this periodical crystal lattice, and the minimal volume and the lowest amount of the atom, where I can represent the lowest volume in one atom, means that I have the primitive cell where I can repeat of this space and have the unit cells and the crystal lattice cells. So the primitive cell can be organized by these primary vectors, and the linear combination of those vectors, we can describe any position of the atom in the crystal that we are seeing. So to seek the primitive cells, we use the Wigger-Cies construction, and this was what I was talking about. To seek the position of the primitive cell, we must dimension the two the lines between the nearest atom of our center atom. So in this case, that are 2 dimensions, so it's easy to see. But after we draw this distance between the atom, we can we must draw a perpendicular line over those distance between medium distance of the distance of the atom and the square that are identified over the region that can be filled. Inside the second square are the Wigger cells or primitive cell. So here we have primitive cells, here we have unity cells. So it means that not every unit cells is primitive, but every primitive cells are unit. And in 3-dimensional, this is quite hard to see if you can have some different arrangement of atoms. And when we go to 3-dimension, for example, we usually replace those primitive to see for crystallography, for example, with planes, and analyze those planes of the unity, the primitive cells. But what are the most important things to think on unity primitive cells? That we can study a single representative volume and spread like a generalization of the whole material using one single volume. So it usually, primitive cells, it usually used for modeling. We can use just a small quantity because of the number of the atoms that we use in the simulation, for example. And when we go for crystalline analysis using crystallography, for example, you usually see unit cells that are more than one primitive, are the primitive cells, but in large size. To study one single primitive cells, we must study one single atom, which is kind of hard to synthesize it in the laboratory. So the most important thing for electronic devices that the distance between the lattices of the materials impact on the energy, state energy, on mechanical properties. So if we have this this information on primitive cells, we can also predict how it could be over a large amount of material. And if we don't have any breaking, any disorder in the trap between the materials. So the primitive cells are usually used through simulation, where I can, for example, seek new material that could have different performance and different properties that could, for example, one semiconductor that is not available, but we can predict using quantum mechanics and the unit cells. Here, for example, are the Brava lattices in 3 dimensions. Here are for one example for cubic system. So if we can organize it, the materials in different geometry, depending of the length between the unit cells, for example, here. And we can also see that the organization can be inside, for example, the cubic could be different replacement depending of the primitive cells. And this could be cubic, simple cubic, cubic for body-centered cubic, face-centered cubic, for example, in cubic crystal system. But we have 14 distinct Brava lattices, and these lattices are classified in 7 different systems. And here, for example, the cubic are the most popular for materials, but when we study, for example, perovskite, we have this tetragonal geometry, and but perovskite can also organize in cubic system. But for semiconductor material, we have tetragonal, and for cubic system perovskite, we have insulator properties. So depending of the geometry of atoms, it will impact of directly on energy between those materials. And the another popular lattices that are used in electronic are diamond or zinc blend. Here I put and I didn't see that was covered, but the diamond are the construction of ions, the atoms that are one of most stable. So we have this cubic structure with face-centered cubic lattice, and this can be seen in here. I didn't put, but the silicon, for example, can be used. The silicon organization are the diamond lattice, and also the carbon using sp3 hybridization, and germanium arsenide. They also are organized in this geometry, but they are called zinc blend because they are 2 different materials that are organized in order to have this geometry. So these are the most stable structure. This is the reason that silicon, for example, are used as the most expensive material for semiconductor. And when, for example, we want to high efficiency, high stability, we must use this structure. And if we want to decrease a little bit on stability, we can use gallium arsenide. And for example, to send it on satellites, it would be better that to have a higher efficiency and higher stability than cheaper materials. So depending of the application, we seek also the materials that we are investigating. So they have that tetrahedral coordination, and for nearest neighborhood per atom, this can generate a covalent bond between the atoms, and this affect their stability. In terms of plans and directions, we usually represent the crystals using those Miller indices. These Miller indices are the indices that define a parallel lattice planes. For example, here, if we have this cubic system material that are organized in cubic crystal, we have this plane that is 0, 0, 1, which means that they are parallel to x, I, and the cross the z x. And another kind of Miller planes for cubic system are, for example, 1, 1, 0, 1, 1, 1, and 1, 0, 0. And here, if we have one plane in half of distance between the atoms, we have the 2, 0, 0 plane. What is important to study of Miller index? Because depending of the plane that we are seeing, it will directly affect the crystallization of material that you can, for example, deposit over those planes. If you have, for example, one silicon 100, your material that are upper those planes grow differently than the plane over the 110 and then different than 111 plane. This also affect the atomic pack density. So when, for example, we have diamond and we want to do a small diamond, how we can cleave some diamond if they are very mechanical stable. So we must cleave those diamonds in some specific planes. So depending of the plane that you are seeing, you can have some mechanical and electrical and thermal properties specific for those planes. So I talk about the materials and how they are the atoms and how they interact with each other. I just gave an overview. It's not so focused on the solid state principles because of the time of the course, and the focus will not just on the theoretical point of view, but also will be applying those materials on electronic devices. And in order to give an overview on organization and correlation with the devices, the materials are previously organized in these four type of materials. But when the materials started to increase in 2000 around, different properties were seen, and I think it's hard to classify materials with different properties, because sometimes, for example, 2D materials they can be classified with single crystals, or they can be classified as polymers depending of the interaction with another neighborhood atom. So it's hard to classify materials with properties. I'll just give an overview on the most popular materials for electronic devices and how we can form those materials to see in real world. So single crystals are, as I told, are perfect periodic lattice with longer range of organization. The symmetry between the primitive cells and the unit cells are governed by block states. So we can spread the density of state with all the atoms. And they also have minimal defect density. So we don't have any defect during the production and defect during the crystal growth. Instead, I want to introduce this defect in the single crystal to analyze it. But with a single crystal, we can construct, for example, just one crystal of silicon, and without any doping on those atoms. So to have these single crystals, we can use different growth techniques, which are called Bridgman and Kuchowski. I don't know if I pronounced it properly, but the basic procedure of crystal growth are disposed here. So we have this single crystal of silicon, and here we have silicon melt. And depending of the thermal gradient that we have here, it will grow on the the film will be deposited on this surface that will be perpendicular. So it will depend on the heater, the rotational, and also the stability of this melting, if not contaminated. But this is one figure, representative figure of the technique to use a single crystal. And this technique is quite expensive because we must have a really clean room. We don't have any contamination. And also the gradient of temperature must not be exceed, because any difference on thermal gradient inside the shield here will directly affect the crystal growth. And these materials are basically used for microelectronic compounds. So, for example, some devices that are quite expensive or supercomputers, they use the silicon single crystal, as a semiconductor for transistor, for example. Here are materials classified as ceramic and glasses. So the ceramic and glasses can be inorganic, amorphous, or polycrystalline, depending on the organization. And they have a high melting point, usually have a high melting point, and isolate behavior depending on its structure. For example, here we have the perovskite, and perovskite are usually described as isolator, but using inorganic and organic perovskite, we could reach this energy gap between the energy states in the region of UVV, in the region of visible light, and can be used as semiconductor. So depending of the atoms that we could arrange in this lattice, we can have isolant properties, or we can have semiconductor properties. So they have usually ionic or covalent bonding strong. And as I told you, amorphous don't have any order, but in polycrystalline, we must look into grain boundary, which means that, for example, here, if we have some film made by ceramic perovskite, this, what we can see here are the grain boundary of the crystals. So in order to have better, for example, charge transport, we must have lower grain boundary, because each grain boundary means that we have charge accumulation in those interfaces with just these different lattices. And also they have usually, depending of the technique used for the position, but we can control the defect in charge trapping. The polymers are another kind of materials that can be used for electronic and optoelectronic devices. So here I classified polymers in two kinds of polymers. Maybe we can also classify in several more, but here are more isolated properties and the ionic charge transport. But in here we can classify the polymers as conjugated polymer, which has different structure. So starting for isolator polymers, we have this PVA, cellulose, PVDF, PMMA, which are the most popular isolate polymer. This polymer could be used as substrate, as some sealing for improve the stability of materials, and also can be applied in different kind of different part of devices, electronic devices. But in general, the polymers has long chain, and this long chain can be organized amorphous or semi-crystalline, that is not crystalline but is analogous with crystals, and like crystalline polymer, where we can have semi-crystalline, some regions that will have a repeat of the unit, or in kind of crystalline, the number of repetition will be increased. Not that they are crystalline in terms of states, solid states, but they are more crystalline than amorphous. So this disorder we can also use, and there is a beauty behind the disorder, which can be somehow applied for the electronic. And we have a strong electron phonon coupling between the electron and the phonon of the polymer. And regarding the transport, we usually using hoping through these states. In this case, isolating polymers, they are, as I told you, most used for substrate and some material that we can use as basis for sustain the electrical devices. In terms of conductive polymers, we have these conjugated polymers, which means that carbon are here hybridizated as sp2, and they have some delocalization of electrical cloud over all the carbon units. So this delocalization, we have a smaller energy gap between the high occupied states and the low unoccupied states, and this we can have the energy between the energy gap, analog gap of inorganic, but we can have indivisible light. And depending of molecular backbone, which means if I have some kind of order, I will have the localization, more the localization than if I have some random. But I also have a charge transport interchain. For example, if you have polymer here and have polymer under, we can also hope between these states, and these are the most attractive for these materials, and they are usually used as transistors and flexible electronics. So here one example, the conjugated polymers that are popularly getting increased investigation are the developments of wearable devices where we can monitor it, for example, the blood rate and some medical aspect together with the electronic properties. So as we can construct it in flexible substrate, we can also apply for lightweight devices. So in terms of charge transport type, we can organize the polymers in filled polymers, which means that we mix some isolator polymer, for example, PANI or PMMA, and we dope it with carbon nanotube, for example, and we have the filled polymers and the transport between those doping molecules that we put on there. And we also have ionically conductivity polymer, which are they usually governed by oxide and redoxide regions, where we can construct electrochromic devices, or we can construct some membranes for sensor pressure, for example. And charge transfer polymer and conjugated conductivity polymer that are the most used for photovoltaic and LED devices. Here are one of the applications. We can use, for example, for energy storage, for food processing monitoring, and for healthcare, organic solar cells, organic light emitting diodes, or smart test tubes. The liquid crystals are the kind of materials that are not neither solid neither solid neither liquid, so they are between the organization of solid and liquid. They were mostly used in TV, so we have these materials applied as semiconductors of TV. But I don't know if you have in room, so in your home, these TVs. But when we have some kind of higher gradient of temperature, this crystal liquid stopped the working because they increase it too much the higher the temperature, too much high the temperature, and the temperature governs the material's orientation, and also it impacts on some specific, for example, energy gap between the molecules. We is not so much seen in the LCD was replaced by LED, that was more stable. That is more stable, but we can also see this kind of material on displays that need this thermochromic or sensor that needed these thermochromic properties. So when we have this chip energy gap, depending of the temperature, we can investigate the LCD, for example. And the last material that are emerging material are the 2D material, which can be 2D in terms of organic 2D materials, metallic 2D materials, salts, non-organic, purely inorganic materials. So depending of the atomic bond between the lattice, we can have different properties also. And the 2D materials are well organized, and they are usually a few layers. So we have this peculiar of the 2D materials that we must have 2 or 3 layers of the unit, the repetition unit in ZX, but in plane we can have a huge plane, it's not a problem, but in ZX we must have two few layers. This is quite hard to obtain because of the technique used to grow the films, the materials, but they are really getting focused on the properties, and they have high mobility in quantum confinement effect, depending of course of the structure, and the preparation of films. They could be usually by mechanical exfoliation, where we have the huge crystal and we can spread over one substrate due to van der Waals interaction between those planes. So van der Waals interaction are weak, and we can break it just using mechanical stretch. We can see it when we draw using pencil, not pencil, but I don't know in English, but graphite. We can do like a graphene using just spreading the graphite over the paper, for example. So if we have more layers, the properties will increase significantly. So the 2D materials, this is the reason that they are called 2D, because we must have a 2D-like structure. They also can be growth using CVD or MBE, epitaxial monolayers. And they are also investigated using solution-based deposition over flexible substrates. In terms of deposition of semiconductor films, I will just give a quick talk about it because of the time. We have this kind of depositions that I would like to give an overview, but we have several types of deposition in film formation. But for semiconductor thin films, can be both high inorganic or anorganic materials over on substrate. It will depend on the substrate orientation. For example, if you have some amorphous substrate, the material that you spread over those substrates will have a more proportional amorphous structure than organized, because the seed of the crystal growth will be follow the seed of the substrate. So in terms of the deposition method, if we have more ordered deposition, we must go to the most ordered deposition, that is epitaxial growth. And we have a high crystallinity on material that we use it. And if we have disordered and we want to have disordered film, the most technique that are disordered is the technique called the solution process, which cause low polycrystalline materials and increase the traps in scattering and reduce the mobility. Although these two kind of deposition techniques are quite different each other, because as you can see, the epitaxial growth here requires equipment that consumes a lot of quantity of energy and cost. I'll just give a quick overview here. And the solution-based filming that we are working nowadays. But as I told you earlier, there's not just spin coating or blade coating, but also different kind of deposition. For example, screen printer, inkjet printing, or chemical bath. These are most applications for organic film films and flexibles, electronic and sensors. There's not just these two kind of deposition of materials, but there is several kind of material deposition, depending on physical deposition or chemical deposition that you want. You can have, for example, physical deposition using vacuum evaporation. Most popular is resistive heating, but has electron beam, laser evaporation, and further. Physical techniques to form thin films are also classified with sputtering, IO beam, and another magnetar sputtering, for example. When we go to chemical deposition, that we have some chemical interaction to form the film, but the chemical will not be included in the film. We can see vapor deposition, laser vapor deposition, plasma vapor deposition, or in liquid phase, this in gas phase. We can also have this different kind of deposition. Each deposition has some the peculiar properties. They will have some different material if you compare just the film formation and use the same material. Some of materials cannot be applied, and another deposition. So sometimes the relationship between how to construct of devices, it also a challenge in how to construct the films to construct the device. So I think it's all for today. I talked too much actually, and here are my contact again, and I see you on the next Tuesday at the same time.